Assalamualaikum. Hi, and a very good morning for everyone. My name is Muhammad Khair Afham from School of Business and Economics. I'll be your moderator for today's session. Welcome to another series of webinar brought to you by CADe, Center for Academic Development, University Putra Malaysia. So for today's title is Longitudinal Data Analysis in Educational Research. Right. So for your information, we are live on Zoom and YouTube. So if you have problem with your Zoom, you can always go to YouTube, just search CADe UPM. And while we are at it, make sure you subscribe to CADe UPM YouTube channel. You can also watch previous webinars. For example, for last week, we had CADe has quantitative research design, descriptive and correlational research. So go to CADe UPM YouTube channel and subscribe. Format of this webinar is the trainer will make his presentation. You can raise your hand to ask question on Zoom, or you can type in your question on Zoom, or you can wait until the end of the session for our Q&A session and ask your question whether in Zoom or in on YouTube. Our trainer for today is Prof. Lau Siong Hook, and allow me to read a little bit about him. Professor Dr. Lau Siong Hook is from School of Business and Economics, CPM. He holds a PhD in economics from University of Leicester, United Kingdom. Currently, he's teaching time series analysis and forecasting, econometrics at graduate level, and introduction to econometrics and applied econometrics at undergraduate level. He has published more than 130 articles in refereed journals, 56 in Web of Science, and 114 indexed in Scopus. Most of his published papers utilizes panel data estimation methods and time series analysis to address issues in economics and finance. He is actively involved in research activities, and his research has also granted him several awards, such as top 2% scientist in the world in the field of economics. He was also the winner of Malaysian Science and Mathematics Society Original Book Award in 2019. Currently, he is the editor-in-chief for International Journal of Economics and Management. He's also a member of editorial board for Economic Systems, Q1, Capital Market Review, Journal Economic Malaysia, associate editor of Emerging Market Finance and Trade. And so let's welcome him. And Prof, are you there?
Yes, yeah.
How are you, Prof? Are you ready?
Yeah, I'm fine. Thank you. Yeah, Dr.
Yeah.
Yes.
Are you ready? Yeah. Okay.
Yeah.
So without further ado, we have Professor Dr. Lau Siong Hook to do his thing. Welcome.
Yeah. Okay. Yeah. Thank you, Dr. Pham. Salam sejahtera and a very good morning, ladies and gentlemen. Yeah. Thank you for joining this webinar session. First of all, I would like to thank CADe for having me to share this topic. Let me share my screen. Yeah, I hope everybody can view my PowerPoint slide. So the title for today webinar session is longitudinal data analysis in educational research. Yeah, so I will start the learning outcome. Yeah, so yeah, to understand the detail about longitudinal data, but sometimes we call this as a panel data, and to compare this type of analysis with other quantitative analysis before applying it in our research. So I believe that we have different background, different area of specialization. Then we can collect the data, then we can analyze using the method. So the outline of my presentation consists of the first I would like to highlight the structure of the data. We have time series and also the cross-sectional data and the longitudinal data, the one that our core business today, or sometimes we call this as a panel data. And benefit of using the LD, use the LD stand for this longitudinal data. And some example of application, then the basic estimation using the data software. Of course, there are many, quite a few software we can use, not only the data, but for example, the MATLAB, the R software as well, and also other like the Gauss, and also the SaaS example. Yeah? So not only the data we can apply in this, but also other software can apply in our estimation. Yeah, so I'll start with the time series data first, then move to the cross-sectional. Yeah, the time series data is observation on one or several observation or variable over time. So the time dimension is very important here. So the sequencing order and can have a different time that frequency. The sequencing important is here. So we have the annual data. Let's say this is the yearly data, and quarterly data, monthly data, weekly, daily, hourly, or sometimes now we have even higher frequency every 50 minutes with one observation. So the example can be our unemployment, how many percent unemployment rate, and then the inflation rate, and also the stock prices, so on and so forth. And when we enter the data in our spreadsheet, let's say in Excel, we will enter in the column, yeah. Then we can plot the time series graph. For example, on your right-hand side is a Malaysian real GDP, gross domestic product per capita, our real income per head count. So yeah, it's increasing over time, but due to the COVID-19 pandemic 2020, yeah, the data is until 2020. You can see there is a drop, the GDP per capita. So normally when you see when we read article, the journal article, normally the equation, the mathematical equation, they will have the subscript T. So when you read this, see their equation or the model, you see the notation here is T, then it means that the author used the time series analysis. The second one is the cross-sectional. Yeah, we only have a sample of individual, let's say individual, the student example, or household, firm, country, region, city, and other type of the unit. And we only have one specific point in time. So I mean that each unit here, they only have one observation. Yeah, we can take the average. For example, let's say 10 year, last 10 years, then you take one average 10 year, we have 1 point. But we need to be aware that the data across all units do not correspond to exactly the same time period. Let's say the company listed in our stock exchange, the Bursa Malaysia, just recently listed, let's say 3 years compared to the old company they have listed 10 years ago. So we can take 10-year average and also 3-year average, not mean that they must have the same 10-year all across all the company. Yeah, we can take different time sample period to get one average value or you also can have one observation. You can take 2020. Yeah, that one is represent the cross-sectional across the firm. So when we enter in our Excel, we enter in terms of the row, vector or row. Yeah, let's say one row represent one firm or one row represent one individual. Yeah. So on the right hand side, I plot the scatter plot, the relationship between our real GDP per capita US dollar, and then the number of the hospital bed per 1,000 people. Yeah, so whether higher income country, they have more hospital bed here. So we can notice that Japan and Singapore, they have quite similar income. Yeah, you can see they have quite similar at around 40,000 USD, above 40,000 USD. But in terms of the hospital bed per people, per 1,000 people, Japan seem to have higher. Japan has the highest, then ranked by Korea, and then the Singapore. And Malaysia is in between here. Yeah, Malaysia, you can see in here. All right. And other Asia country, East Asia country. So this is the cross-sectional data. So we move to our core business today is the longitudinal data, or sometimes we call this as a panel data. Yeah. So it's denoted, yeah, just now the time series, the subscript is T, yeah. No, the cross-sectional is I. Yeah. When you see the equation is I, mean the author used the cross-sectional data. All right. And come to this panel data, they have the IT, two-way or two component here, cross-section plus the time series. So it's a combination of time series data and also the cross-sectional data. Yeah. So the observation on the same unit mean that we need to observe the same unit throughout the year. Yeah. So for example, can be the unit can be the people or individual here, or firm, city, state, markets, or country. Yeah. So this is our unit of the study. You want to study their behavior, yeah, subject to our area of specialization, yeah, in several different time periods. Can be annually data or quarterly. So normally the panel data tend to have this annual data or quarterly data. If let's say we have high frequency data, or let's say monthly, we have 5 years, then 5 times 12 and 60 observation. Maybe you want to carry out the study using the time series analysis, not the longitudinal data or panel data analysis, right? Yeah. So this is the mean that we need to have the ID to record the ID. Then we observe that person, the people or firm throughout over time. Yeah, the sample period that we have decided. Okay, so these are the few examples. Yeah. Example, the panel data or the longitudinal data on spending pattern of individual behavior over the life cycle, yeah, throughout over the last 5 years, the consumer spending behavior, yeah. And in terms of the firm or company data, we can look at the sales and the number of employee for 50 firms over the 5-year period, 2001 to 2005. So the time dimension is 5 years, 2001 until 2005. The cross-sectional is the firm, yeah, 50 firm. So we observe these 50 firm, the same firm over the time period. And we look at the comparative country specific macroeconomic study, mean we want to compare across the country, then we can get, let's say, our GDP, our output, and the government debt data for a set of 10 countries for 20 years. So this is also the panel data, yeah, because they have 2 dimensions, the time as well as the country. Mean the cross-section is for the country. Right. So in terms of the data set, the well-known data set in the world. So normally we have the panel study at the income dynamic, PSID. So they have the GDP across the different country, unemployment across the different state, income dynamic study, yeah. And the macro, we also have the Pan World Table, and also the World Development Indicator by World Bank. So they have all this information, the World International Trade data, and also the socio-economic table, and also the exchange rate table. And then in terms of the medical expenditure payments survey, you have this public health, insurance data, disease survival rate data, child development, and the well-being data. Yeah. And of course, in the area of finance, we have the stock prices by firm, market volatility. So of course, we can get from the global market indices and also the data stream. Yeah. So I believe that you know where to get the sources of the area of specialization. Yeah. Maybe we have the sample cross-sectional, but we need to observe over the time period, not only one single year or average, but we want to move more forward to look at the more dynamic, mean that collect more data observation to see the behavior of the pattern of the unique. So when we enter the data in our spreadsheet and the Excel, so we enter based on the, okay, the individual one first. Yeah, so for example, you can see this is our variable, the Y, and then after that, other variable. So from the time period 1 until time period T, you start from the time period 1, let's say 2000 until 2020. Then the second individual means we stack the data. Yeah, after the individual one, then we present the individual two data set. Yeah, so we have the same variable, and then start from the time period 1, time 1 until the time period T. So to indicate that, okay, this is the end of the sample time dimension. And then we stack again for the individual tree. Yeah? So it means that we keep continue for this format, then we will form the panel data. So normally the software, they can reshape the data. So let's say you get the data in terms of the row, they will convert to the column for you, variable by variable. Then you can transpose, then you can form this type of the data. Yeah, don't copy and paste because that one will take a long time for you to formulate the data set. Then yeah, so please the software, they have the guideline. Then we use a software code to come out with this type of the data or panel data or the longitudinal data format. So mean that you keep on stack the individual 1, 2, 3 until let's say we have 100 individual. Okay, yeah, right. So this is the based on the, let's say I have the 4 students, yeah, on the name of the student, and then the time dimension, of course, is based on the semester 1 and semester 2. So let's say I have the 6th semester, throughout the 6th semester in terms of their CGPA, their performance, the student performance, and the hour, number of hours they study per week, as well as the number of credit hours they have taken per semester. Yeah, so this is example. You can form a panel data set for you to analyze the student performance example. Of course, not only depend on these two, but other factor also will be important. Yeah, affect the CGPA, the student CGPA. So we have 6 semester, mean we have the time period is 6, and the cross-sectional dimension is 4 students here. So of course we can add more students, yeah, in one, let's say in our class, then we can have their result. Okay, so I move to the next one. So yeah, then you can plot the example. Let's say you have these 4 students. You can plot the scatter plot. Yeah, let's say the relationship between the CGPA and the number of hours they study. Then you can see that maybe this is the scatter plot for these two variables, CGPA and the number of hours study. Then after that, you can model, you can draw a linear line to model the relationship between the CGPA and the number of hours study. Yeah, because this is the bivariate two variable, the simple linear regression for the panel data. Yeah, later I will show you some estimation. Okay, so this is what we have for the, the LD, yeah, or panel data. Okay, so the summary here, the longitudinal study, we study the paper, measure repeatedly over the time, yeah. So mean that you want to see the people, how they behave over the time, whether let's say the income has been improved, yeah, the income, uh, their salary example. And then the cross-sectional study, mean that we have the cross-sectional in terms of the people. The single outcome is the measure for each individual. And in this panel data or the LD analysis, we can examine the changes over the time within individual. We call this as an aging effect. Yeah, because over the time, their age getting older, therefore we can see the aging effect. And the difference among the people in their baseline level, or we call this as a cohort effect. I mean, a group of the people with a shared characteristic. Yeah. So the LD analysis requires spatial treatment or statistic method because the set of the observation on the subject tend to be intercorrelated. So this violates our classical linear assumption. So therefore, we need to overcome by using the proper estimator so that they wouldn't have any issue, yeah, correlated issue. Later, I'll show you the assumption of the classical linear assumption, whether they have to violate the assumption, yes or no. So example, we repeated measure made on the same subject will be correlated. For example, John, yeah, his cholesterol level in 1989 will be related to John cholesterol in 1990. Yeah, so mean that, yeah, they have the lag effect example. Yeah, I mean, for example, this year is not only this year is affected by last year. Yeah. For example, the performance of the student this semester might also influenced by the last semester performance. Example. So now due to the online teaching, you also can study whether the online teaching method have any impact on the student performance as well. Yeah. So for let's say you have John, Jane, and Jim here. So the Y11 one stand for the I, the individual, and then the another one is the year 1, year 2, and year 3, and the 2 or the purple color is the stand for Jane. Yeah, so I the cross sectional is for Jane, so it's 2 2. Yeah, then after that it's 3 3 3 3 for Jim. So this one type 1 mean that in the year 1, of course, yeah, for John himself, the cholesterol level will be affected by the previous level. Yeah, so this is called the dynamic process, not the static. Yeah. And the panel data or this LD, they have the two common features because there are a large number of individuals observed and only a few time period, mean that the number of the individual is greater than the time dimension. So we call this as a micro panel or the short panel. So n can be, let's say, 100, 500, or even the 1,000. Yeah, it depend on your sample. Yeah, and then the second is there are some medium length time series from relatively few individuals. Example, the country study, the state, the firm. Yeah, so mean the T is greater than N. Mean the time series dimension is greater than the cross-sectional dimension. We call this as the macro panel or the long panel. So the long panel here is referred to the T. And just now the first one, the short panel is referred to the T as well, mean the T is short. Let's say only 10 year or 10 observation. Yeah. So let's say we have 50 time series, 50 year, you can take the 5-year average. Then you divide by 5, 50 divided by 5, then we only have 10. So we can reduce the T by taking the average. Yeah, so this is how we can modify whether N is greater than T or T is greater than N. Because the estimator we want to use depend on these two characteristics. Yeah. And then we have the balanced versus unbalanced or non-balanced panel data. So balanced panel means they have the same year. Let's say they start from 2000 to 2020. Yeah. All the sample, the cross-sectional unique, yeah, the cross-sectional dimension, they have the same year. It's a balanced panel. But sometimes they might have missing data few years. Maybe 2 years, they do not have this observation. Maybe some cross-sectional unit, they start from 2005 to 2020. So mean this is unbalanced panel. They are not have the same year over the time. Example, this is based on the state, Malaysian state data. We have the Kedah, Kelantan, and Selangor. So this is actually is the real data. Yeah. So the GDP, the output of the gross domestic product, also the FDI inflow, the foreign direct investment, okay, flow to Kedah, Kelantan, and the Selangor. So you can see that this is the balance panel because they start from 2005 and then they end the year 2008. So it's the same T observation 2005 until 2008. And the unbalanced or non-balanced panel data or LD. So for example, Kedah we have four years, and then the Kelantan we have 3 years, and the Selangor is 6 years. So this is an unbalanced panel. Yeah, so different T observation. So although they have a different T the year, the data can analyze this unbalanced panel. Yeah. So don't worry, even though we are missing some year, the software, they still can take care of this unbalanced panel because we give a signal to the data. This is the I, the cross-sectional unit. This is the T, then they can identify whether it's a balanced or unbalanced panel data. Okay, so now I move to the benefit of using the LD or the panel data. The first one, normally when you read any textbook or the talk about this, discuss about the LD and the panel data, they will say we can control for individual heterogeneity. Yeah, so many individual, the student as well. Yeah, characteristics are not the same, not observed. They are not the same. Yeah, of course, different individual they have the different skill, ability. So, for example, for the investor, yeah, whether they want to invest, their enthusiasm or their willingness to take the risk also represent the characteristic of the heterogeneity. So this vary across the individual. So we describe this as an observed heterogeneity. I mean that the specific effect, yeah, for this individual. So different individual, they have their own specific effect. Mean the heterogeneity here is referred to the micro unit are all different from one another in fundamental measure way. So it's very hard to measure this. For example, the household taste and preferences. We can't easily measure the taste and preferences, whether they like it or no. Yeah, so we tend to assume that, okay, this is put in our residue, yeah, the error term to capture these taste and preferences. Yeah, so in this case, for the first controlling for the individual heterogeneity, So it is inferred the variable of interest, yeah, due to and correlated with the observed our x variable, the independent variable, then the estimated effect of this variable will be biased. Yeah, let's say they tend to correlated, they infer each other, then we cannot get the robust or reliable result. So the solution with the LD or the panel data, we can take the differences with respect to the I average, because this is within transformation or called the mean method. I mean, let's say for the variable y, we find the mean of the y, okay? Then the mean of the y, they will minus its observation, then they will turn to another value. So we use a d mean, I mean that we take the minus the mean of the y. So if not only the y, other variable, the x1, x2, find the mean of x1, then is x1 minus the mean of the x1. So this is the mean process. So when we take the d mean process, we will get rid of this heterogeneity. So all are equal. So we can analyze the data because no more heterogeneity or specific effect. Or the second one, we want to take into account of this specific effect. We can use the least square dummy variable. You put the dummy to represent each individual or each country or each state. So we have the specific dummy to represent each individual. Then because we have this method will won't kill or won't delete or transform the first different, yeah, or the mean data. So we have more, the information won't be lost in our data set, yeah. So without killing the data, it's specific to the I and also or the T. So this is the solution in the LD and the panel data in order to overcome this heterogeneity or specific effect. And the second benefit using the LD, we have more information data set. Of course, we have the larger sample size due to pooling the individual and the time dimension together. Yeah, we get more info. We have N, and so the T, more N, more T, more N. Then we multiply with the T. Of course, we get the larger sample size. So let's say N times T, total observation, yeah, for the balance case. And then, of course, when we have more information data set, we have more variability. Yeah? So, of course, we need more variability, the data set. Let's say the data is more or less the same, no variation. Of course, the information won't be able to analyze. Yeah? So, more variability, we have less collinearity. Mean that in terms of the multi-collinearity, we tend to have no multi-collinearity issue. Yeah, it's often the case in the time series for the collinearity issue. Yeah, especially for all the independent variable. And then often the relation between unique, yeah, based on the cross-sectional dimension, is much larger than the relation within unique. And so normally, because across the unique here, let's say the country like Japan, Singapore, they have the high income per capita. Then the sample, we have the Malaysia, Thailand, Vietnam, Cambodia, Laos, Philippines, Indonesia. Therefore, in terms of our GDP per capita or GDP, then the relation tend to be higher across the cross-sectional. But in terms of the variation within unit of the time series, normally the variation smaller is much smaller within the unit itself. Let's say Malaysia GDP per capita. Yeah, each year is increasing. Yeah, every year we increase our GDP per capita, so the variation will be much smaller. But across the cross-sectional perspective, then the variance will be higher. Yeah, the variation between the cross-sectional will be much higher compared to the within or time series dimension. The time series only one country. Yeah, so one country, their income or any variable, especially the continuous or discrete data, normally the variation tend to be lower. So normally when you observe the panel data, you can see the between variant, the variation is much higher than the within variant. So later I will demo to you how we can get the between and within variant using the data. And then better to study the dynamic of adjustment. Yeah, so the cross-sectional data can tell us nothing about the dynamic, whether the past information affect the present or current information. Yeah, but the time series data we need quite a lengthy time series data to provide a good estimate of the dynamic behavior. Yeah, mean the past information affect the current behavior. But the panel data or the LD, they observe the same individual in the different period, different time period. So avoid the need for the lengthy time series by exploiting information on the dynamic reaction. Yeah. So only the panel data or LD, they can model how individual adjust over time. Yeah, mean that we observe same individual over time. Yeah, this one is based on the household survey. Our those are the Department of Statistics Malaysia. Now they've started to collect the panel data because previous the household survey they did not assign a code, then they cannot trace the same individual. So now they can use our IC number to trace the same individual over time. Yeah, so you need to fill out our IC number so they can observe the same individual over time, because this is very important for the policy evaluation and also the life cycle model for whether we have the better income or the better well-being. Yeah. And number 4, this identification of parameter mean the beta we want to estimate would not be identified with pure cross-sectional and also the pure time series data. Example, whether the online learning affect the student performance or does union membership increase worker wage. So this is the 2 example we can analyze based on this using the LD. So the LD allow to model both, for example, the online learning and the union membership. Yeah, and also the individual characteristic for the individual who enter the online teaching and also the union membership during the sample period. So we can have the before and the after. Yeah, before they enter the membership, join the union, or before they have the online learning, and after we have to conduct online due to the pandemic. Yeah, so this is also observe the same student over the semester, throughout the semester, before and after the online learning. Then whether in terms of their result, the semester result tend to become better or not so good result. Yeah. And then this is another is based on the economics of area, economy of scale. Yeah, mean that they can operate in the lowest cost. Yeah, whether the production can produce with the lowest cost. Yeah, and also whether the firm they evolve throughout the time based on they use more technological, use a more advanced technology. Yeah, technological change in the production process. Okay, for the cross-sectional data, because can only use to examine the economy of scale, because they compare the big size and the small size firm, and compare the cost of the small and the large firm. But because all the data come from one time period only, because only one observation per firm, so no way to estimate the effect of the technological change, because technological change need to have the time series data, because the firm become perform better now due to they use the technology, more advanced technology. So we need to use the time dimension data to see this effect. Therefore, the time series data on a single firm, only single firm, we can observe the technological change, yeah, due to the change in the firm, in the size of the firm. So the firm performance become better because they use the more advanced technology. But when you combine both, you can want to, if let's say I want to look at both perspective, I need to use the panel data. Yeah. So panel data can deal with both the economic scale and also the technological change. All right. So I think that's all the benefit of using the panel data or LD. So finally, we have the advantages of LD or panel data. We have more observation, more degree of freedom. Then we also can reduce the multi-collinearity, yeah, because we pull the cross-sectional and also the time series data together with more big data, yeah, and so more observation. Then this will improve our estimation efficiency. In the estimator, they are unbiased and with the smallest variance for all possible true parameter value. Yeah, so these are the outcome, yeah, when you use the LG or the panel data analysis. Okay, I want to recap a bit for our notation used in the equation, yeah. So the cross section, like I mentioned just now, they use I to represent the equation, yeah, is non-order, yeah, but the time C they use the T is order, mean that they need to follow the sequence, yeah, the chronological is important here. And then we have the Y is the dependent variable and X is the independent variable. So we have the simple linear regression. This is the cross section. You can see the subscript is I, and the time series their subscript is T. Yeah. So this is just a simple only one X. Of course, in our estimation, our analysis, we need to have the more than one X or multiple regression model, yeah, or multivariate here. And then we would like to estimate the alpha and the beta. Yeah, the purpose is to get the alpha and the beta. Then after that, I want to see whether the X is important or significant determinant of Y. And whether this X variable is important determinant of Y. Yeah. So we have the X1, X2, X3, X4 example. This X is important, yeah, in terms of the positive sign, positive relation, negative relation, in terms of the sign, whether the coefficient is big, yeah, in terms of the elasticity, the percentage change is large, yeah. So now I recap our classical linear regression model. The assumption, okay, so the one that I want to highlight is the number 2, yeah, and mean the explanatory variable or the X variable are uncorrelated with the error term. Yeah? So we have the error term, just like I forgot to mention. So yeah, the epsilon here is the error term. Of course, it's impossible to include all the X. Yeah, so other important factor that not identified here will be captured by the error term, the epsilon here, right? So mean that this is our error term or the residual here. So mean the X to uncorrelated with the error term, yeah, mean no relationship between the X and the error term. And then the average mean of the error term will be equal to 0, yeah. So we'll get the mean equal to 0. Normally we have this, the assumption, and also we manage to get the 0. And the variance of each error term is constant. So therefore we call this as the homoscedasticity. If let's say the variance not constant, we call this as a heteroscedasticity. Yeah. So okay, so for the panel data, because for this the variance constant applied to the cross-sectional data. Therefore, we need to take care of this the variance constant or not constant. And then number 5 is the no serial correlation in the time series analysis, our main concern is the serial correlation. So therefore, the panel data or the LD data, they also have the time series dimension. Therefore, we need to look at the serial correlation as well. And then mean number 4 and number 5, these two are the main concern, yeah. And then number 2 will be take care of the estimator, and then the normality of the residual, and then no multi-collinearity among the independent variable. Let's say your model is a multiple regression, yeah, more than one x, like x1, x2, x3, x4. So make sure that the x variable, they do not have any highly collinearity. But for the panel data, normally we won't have this problem because we pull all the data together. So therefore, in terms of the multi-collinearity, I test the result using the variance inflation factor test. So it shows that no multi-collinearity. We concern the homoscedasticity of variance constant or not constant, number 4, number 5. But I need to highlight number 2 as well, x not correlate with the error term. Yeah. So this is in terms of the mathematical expression. And also the violation may imply what? Yeah. So for example, if let's say mean is not equal to 0, the mean of the error term not equal to 0, then we tend to have the bias intercept. Yeah, the across the vertical axis, the y, the intercept is biased because the linear line is not fall in the in the middle of the scatter plot example. And then we have the variance constant, the sigma square must be constant. It's violate, then we call this as a heteroscedasticity problem. And then the serial correlation, no correlation between this year and also the last year error term. They are not correlated, mean the covariant. COV here, covariant, the epsilon t and the epsilon s equal to 0. Mean no auto correlation or no serial correlation. All right. And then this one, the last one is the multi-collinearity. Yeah. All right. So this is the mathematical expression and so the violation. So why is spatial method the LD or the panel data? Because they have the repeated observation. Yeah. Y I1, Y I2 until the Y IN are likely to be correlated. So assumption of independent is violated. Yeah. So if let's say you still use the standard regression method to analyze the data, so we have the consequences here, mean we can have the standard error for the beta incorrect. So when the standard error is not the correct standard error, then in terms of hypothesis testing, let's say I want to test the t-test, because the coefficient divided by the standard error equal to the t statistic. So if let's say the standard error become bigger, then we tend to have the smaller t statistic. So we always fail to reject the hypothesis now, conclude no relationship, no relationship. Yeah. And then in terms of hypothesis testing, so also incorrect. We tend to conclude that no relationship between x and y, but because due to the standard error bias, then consequence here is the hypothesis testing is incorrect. And so incorrect inferences, for example, the p-value, confidence interval, the t-test, f-test as well. And the beta, okay, sometimes is still can represent the true population estimator, but it's inefficient estimate of the beta. Yeah. So this is the result when you use you still estimate using the normal method. Then this is the outcome. Therefore, the result is not reliable. The conclusion also not reliable. Yeah, we need to be careful here. So what is special about the LD and the panel data? We can differentiate the data, the panel data from the cross-sectional effect, and then we will select the several target of the estimation. Yeah, And the challenges is because it's a repeated observation, tend to be auto correlated, auto correlation tend to be appear in our data set. Therefore, we need to overcome by using the robust standard error to overcome the issue. And the correlation must be model, yeah. Okay, the characteristic, because it's repeated observation on individual, and then we have the scientific question is regression method. We use the regression method in this webinar and show the regression method. Of course, there are many other methods, yeah, to estimate the panel data, because our dependent can be the discrete or continuous variable, can be the count data, can be the binary. I say yes is equal to 1, no equal to 0, yeah, using the logic and probability and then yeah, the estimation. Yeah. So that one also can be formed in our panel data. So the dependent variable can be the discrete or continuous variable, can be the count variable, can be the binary variable, the dependent. So if let's say the dependent variable has a different type, then we need to use the different estimator. Yeah, yeah. So what I'm going to share, I use the discrete or continuous variable. So the type of study can be the panel time series study as well. I see the T is greater than N. Then the estimator, I need to use another type, the estimator. The short panel study in the area of sociology, the economic finance, as well as the bioscience, and also the clinical trial, in the health, and also the medic study as well. They also apply this technique in their research. So we move on to the, yeah, a few examples. So I managed to get a few examples from the SciDirect, the Elsevier publisher. So yeah, it's quite a recent paper, 2021. Yeah, so it's an individual learning potential in stressful time, how to leverage intensive longitudinal data to inform online learning. So it's published in the Computer in Human Behavior. So for example, we have this event, the natural disaster, political stability or political shift, and our economic recession, downturn. So it's a time varying and impact the learning potential of the student. And this will create, you know, the whether the student tend to feel very stressful or relax. So this is how the author they would like to study. So yeah, so they use the 75-day intensive longitudinal data study of cognitive, somatic symptom, or this intellectual interest during the 2016 US presidential election. So they identify the presidential election is a period of the quite a stress period, yeah, for everybody in the US. So they have the three methods to estimate the regression, the multi-level, and so one method. So three methods. Then after that, individual learning related processes vary across the student and the time. So they also recommend the method for the future research, especially for intensive longitudinal study of online education during the COVID-19 pandemic. Yeah. So this is the first example. So they have the dependent variable, whether stressful, they put 1, not so stressed, or no stress, they put 0, consider as a binary. Yeah. So you can use the logic and also the probability model to study this. And also they test the student using different various tests, exam, whether they can score, then they feel relaxed, not so stressful. So then they can use the regression or other method as well. And so mean the dependent variable, not only the binary, but also they use the continuous or the discrete variable. Okay, the second example is the relationship among overseas travel. Domestic travel and they trip for Latin tourists using the LD. Yeah, so the study investigate whether the Latin tourists substitute overseas travel with other leisure activity, such as domestic travel. Mean that they not travel to overseas, but they have the day trip, domestic travel. Yeah, because they want to contribute to the tourism industry as well. The one that like happened in the Langkawi as well. So we want to have more, to help the tourism industry. So, okay, so the data, they have the National Survey of Tourism they collect from the year 2004 to 2016. Yeah, all right. So, okay, by the way, let me stop for a while because I need to on my PowerPoint. Yeah? So sorry about that. Yeah. So I need to on my PowerPoint because I said my computer, my laptop run out of the battery. Yeah, they have the 21 subgroup for the tourists. Then they identify based on birth cohort, the household income level. They use the Bayesian logic model. Yeah, so when you see the logic model, mean the dependent variable is 1 and 0. Yeah, so they have the result. You can see 1, 2, and 3 result. So this is the outcome from their research. I don't think I need to go through for the result. Yeah. And the third one is the COVID-19 app and the digital intervention policy. Yeah, the study investigate the South Korea adoption and usage behavior of COVID-19 apps that detect the place where infection people are found and alert people within 100 meter in dangerous zone. So this is the author they try to carry out. This is also quite a new paper, 2021, published in the Health Policy. So the author analyzed the mobile apps usage data from quite close to 6,000 the individual at the start of the pandemic in South Korea after the first major wave on January 6th until August 2nd August 2020. So they find the author they found that higher income and more educated individuals were more likely to adopt COVID-19 apps earlier, and the male and the low-income people tend to use the COVID-19 tracking app more frequently. Yeah, so the study offer empirical evidence on the health protective behavior. So I think it's a very interesting and then a good for the policymaker to survey or to get the panel data. Yeah, I think yesterday the health minister mentioned that one individual scanned the My Sejahtera app. I think it's maybe about 500 times. Even though affected, but yeah, detected have this positive yeah, and then you still scan, go here and go go outside, not stay at home. Yeah, so this can detect the movement of the people. Yeah, so I think it's important to develop the app can detect. Okay, number 4, published in the social science and the medicine here is the role of financial condition for the physical and mental health, evident from a longitudinal survey and insurance claim data. So both theory and the empirical evidence, they claim that the financial conditions are influential for mental health and might contribute to physical health outcome. So they collect the panel data or the LD data as well. So they use the LD data. Yeah, so the sample 1,209 employee in the last US health insurance company. Now after that, they examine the issue, and then okay, they found that the financial safety and the financial capability were positively related, but the financial distress was negatively associated with subsequent self-reported measure of the physical and the mental health. Yeah, so for those who are interested in this topic, you can find the journal using our easy proxy, the library. Then you can download the paper, the full paper. And then number 5 is the relationship of the intake of water and the other beverages if the real, not the real, the real endpoint, cross-sectional and the LD observational and population-based study. So the study, they try to investigate the cross-sectional Lee and also the longitudinal Lee, the relationship of the intake of water and other beverages with the kidney function within an adult. This one carried out in the Italy, Italian population sample. So the data collection at baseline include the demography, all the important info we need to collect using the questionnaire. So they found that intake of the non-water on the water intake did not relate to kidney function change over time, but intake of the non-water did not independently relate to urinary indices nor to kidney function. So this is the result, the finding from the research from this paper. And then the last paper, smoking, this is the smoking behavior, and also the quality of life. So the study take advantage on the LD panel data to estimate the effect of the transition from the smoker to ex-smoker, the quick status. So smoking cessation and also on the health related quality of life measured by SF36. This one in the case of Australia. So they collect the panel data from the 13 wave. So using the mesh, the data set, they have the household income, the labor dynamic of Australia, and then they have the close to 2,000 respondents. And then the result reveal that the very effect of the smoking cessation on the HRQ, the one that they want to highlight, and has a positive effect on the physical and general health, but not significant effect on the mental aspect. So this is the last paper. So overall, what do these examples have in common? They are repeated observation on each experimental unit, let's say the individual. So the example all based on the individual. And the unit can be made assume independent of one another, and they have the multiple responses within each unit. And then they are likely to be correlated, and the objective can be formulated as the regression problem using our multiple regression analysis, and then whose proposed is to describe the dependence of the response on explanatory variable. And then the choice of our model must depend on the type of the outcome variable, whether the outcome variable, the y, is a continuous or discrete variable, or binary, or the count data. So now I want to share the estimation technique, different method of estimation. So okay, so because I think I need to stop 11:30. So then we can have the Q&A question. So first is the full OLS, random effect model, free effect model. And the free effect model, they have two estimators within group and the least square dummy variable. Just like I mentioned, the LSDV. And then we need to perform the diagnostic check for the heteroscedasticity and also the serial correlation and the multicollinearity. But normally the multicollinearity is even happen because of the panel data or the LD data. Okay, the one that I want to highlight is the classical linear assumption is number 2, where the X is not correlate with the error term. Yeah, mean the covariance between the error term and the X is equal to 0, no correlation. Yeah, we must assume no correlation. It states that the X variable should not embody any information about the error term. Mean the X should not contain any information or related with the error term. Otherwise, whether X affect the Y or the error term affect the Y as well. Yeah? So if the epsilon term or the error term here and X were positively correlated, then the estimator coefficient would probably be higher than it would be otherwise has been. So we call this as a bias upward because the ORS would mistakenly attribute the variation in Y caused by the error term to X instead. Yeah? So mean that X and the error term should not have any relationship, no correlation between the X and the error term. So this is the example when we discuss this issue. Our income, our earning, and the schooling. Yeah, the schooling is our education level. So in our regression, we assume only schooling, but of course we can include the year of experience. Yeah, in the one of the independent variable, as well as the square term for the year of the experience, because they might have the nonlinear relationship. Yeah. So in the regression of the earning on schooling, the error term contain the individual inherent ability, which is unobservable but affect the earning. So mean that okay, not only we attend the schooling, the secondary education, tertiary education, but the error term also contribute because it represent our ability. Yeah. So this ability maybe when we attend the university tertiary level, we took the elective courses, let's say, to design the website. And you know how to design the website. Also can do some part-time job to help other company to design the website. And they earn money as well. So this also contribute to your income, right? So however, ability is also correlated with the schooling because you learn this skill when you attend the the tertiary level, the schooling into the university. So mean that the error term and the schooling, these two are correlated, mean they violate the assumption the error term and the X is not equal to 0. Yeah, it's equal to 0 mean they are not correlated. So if let's say they are correlated, mean the covariance is tend to not equal to 0. So error term and the schooling are correlated. Okay, so this is example. So in order to solve this issue, normally the researcher, they would like to use the two-stage least square to find the instrumental variable. They find the parent education as a instrument for the schooling because they believe that their parent education is higher than their children education or schooling also will be higher, whereas the parent education is not correlated with the error term. So now I start the formula for the panel data. So you can see our Y and the beta 1, beta XIT, and the error term. Yeah, the error term here. So actually this is our intercept beta 1. Yeah. So for a variable, we have the X, then we have the mean, overall mean, overall mean. When we have one mean, then we have the overall variance. Yeah, it's called the overall variance. You can see the variance formula. So since panel data have information on both cross-sectional and the time series variation, we can decompose a variable mean into two components: individual mean for unit I, and also the time mean. So the individual mean is just the whole column, the mean of the variable. But the time mean is based on the year. Let's say it's 2000 for all the cross-sectional unit, the mean for the 2000, the mean for the year 2001, the mean for the year 2002. Let's say your sample until the 2020, then you can get the mean for only year 2020. Yeah, so we have the time mean, we have the individual mean. So, okay, we have the overall variance is equal to the within variance plus the between variance. Yeah. And the between variance is the variability across the unit of observation, in that it's based on the cross-sectional variation. Yeah, due to the cross-sectional variation, let's say you include all the same level of the income country or the big firm, yeah, all company, they are categorized as the big category, big firm. Then in terms of the between variation, between variant maybe will be not so obvious, yeah. But let's say include the big firm, small firm, and the medium firm, then the between variant will be higher. Or the high income country, you have the low income country, middle income country, then the between variant will be higher than the within variant because their variation is based on the cross-sectional dimension. And the other one is the within based on the time series dimension, yeah. So they capture how much of the overall variance is due to variability within individual unit. So if the variable does not change over time, through time, then the within of within variance will be equal to 0. Let's say we have one variable, it's a fixed value, constant. Example, let's say the distance between Malaysia, KL and Singapore, the distance between these two cities is over the time, let's say maybe 300 plus kilometer. So over the year, the value will be the same. It won't change over time because the distance between these two cities in terms of the kilometer, they are the same. So that one will be fixed value. It's a fixed value. Yeah. Then if let's say the value is fixed, then no variance because the distance between the two cities, they are the same. Then we have the mean is 300 plus, and the variance will be equal to 0. So let's say I want to test the determinant of the, I use the macroeconomic data to demo here, determinant of financial development across in Asian country. So I have the dependent is the financial development, and also as a function of the institutional quality, let's say the corruption, rule of law, and then the government stability. These are the institutional quality indicator. And the real GDP per capita measure the economic development, economic performance, yeah. And also the FDI, yeah. So these are the three independent variables. So I collect this data from the World Bank, World Development Indicator, 10 Asian country. So I have the 17 year, yeah. Then I need to put in the data, yeah. In the data, so of course you have the country, yeah. All the country, you have the year, start from 1996 and 2012. And then you need to create the ID to represent each unit. Yeah, let's say I put 1 represent China, 2 represent Hong Kong, for example. So let's say the individual data, you also need to create the code. 1 represent the first individual, the second represent the second, number 2 represent the second individual. Then we have the year is a time dimension. Okay, the year you can put 1, 2, 3 until 1, 2, 3 until continue until the last year 2012. That means that you must have the 1996, 1997, until 2012. Okay, if let's say you have the gap, you just put 1, 2, 3, 4, 5 until the last observation for that country. Yeah. So when you use the Stata software, you use the XD set code and year, the Stata will automatically know that this is the panel data set. Otherwise, they will run the analysis based on the normal simple linear regression. Yeah. They won't differentiate. This is the panel data setting. So you can see it's a balanced, strongly balanced panel. So mean that we arrange the data with the code is the ID, So you can use the ID as a variable name or code as a variable name and the year, or you can change the year to time. Yeah. So IT, yeah, not the TI. Don't revert to the T and I. So it's a code first, the I, then T, IT, yeah, not TI. Yeah, so don't reverse. So after that, the data software, they can recognize that this is the panel data. Then we can start to proceed to our estimation, all right? So I think I need to be more, a little bit fast in order to finish the material. Okay, so you can list the country. You want to see the number of country. I have 10 country here. Yeah. So each country, they have the 17 observations, 17 year. So total observation is 170. So in order to see their summary of the descriptive statistic, you use the XT sum. So for the data command, XT, the cross-section time series XT is the panel command or the LD command. Yeah, so you can convert to log, the natural log, then you can see all the variable, you can see the between and so the within. You can see the standard deviation. Then you square root of the variance will become the standard deviation. So you can see the between variance is higher than the within variance, or the variable. Yeah, so you can see between is higher than the within. So between also higher than the within. So this indicate that the cross-sectional variation is higher than the time series variation. Yeah, so between the variation is higher than the within. Between is higher than the within. Yeah. So of course we have one mean only for the variable, and then we have the minimum and maximum value. All right, for the variable. Yeah, after that we can model our estimation, model the how to estimate the equation one. So yeah, we can estimate by using the three estimator, the pool model, and then the random effect model, and the fixed effect model. So these are the three linear static regression. Okay, so the pool model assume that no heterogeneity, yeah, no specific effect, and then no correlation between the error term and also the X, no correlation. So in this case, the data can be pooled, and the ORS, the ordinary least square, can be used to estimate the model. No additional technique is required. So we call this as a pool model. Yeah, beta OLS, the one that we use to estimate the linear regression, the ordinary least square estimator. So the pool model use all the relation, yeah, the time series as well as the cross-sectional. So for example, we brought our panel data, then we can see we can have one straight line, and this is our pool model result. We want to estimate the beta 0 and so the beta 1. Yeah, so that we know the intercept, we know the slope for the X. Yeah, so this is the pool model. So it's valid when the data set in our data set, there's no heterogeneity or specific effect. Yeah, if let's say our data have the specific effect or heterogeneity, we can't use the pool OLS. We need to move on to the next one, either the random effect or the fixed effect model. So for the pool OLS, they have the one intercept beta 0, and they have the one slope beta 1, shared by all the unique here, yeah, the unique here. And then these are the pool OLS model. They have the intercept and the slope, they are the same across the unit and time. So it's quite a strong assumption here. Because why? Not mean that they share the same slope. No, they share the same intercept because due to the heterogeneity or the specific effect. Yeah. So the pool regression may result in the heterogeneity bias. They are often reason why the intercept or the slope may be different, yeah, across the unit and the time. So we need to test whether our data set have any heterogeneity, yeah, using the Bush-Bacon test. So unobserved heterogeneity means our LD or the panel data suggests that individual firm state or country, so and so forth. The unique, they are heterogeneous, mean that they are not the same. They have the specific effect. For example, a panel of individuals might contain different ability or skill, but it's quite difficult to measure unless that person tell us. Yeah, we know how to design the website, and in the firm, in terms of the managerial quality, also not easy to observe, and in the country level, yeah, in terms of their initial announcement, whether the country have these natural resources or, yeah, we are not sure because we haven't, attract from the, from the sea or from the land, example, yeah. So this is the panel data in terms of the country perspective. So mean they have the specific effect or heterogeneity issue. So we need to take care of this. Otherwise, our result will be biased. Yeah, let's say we ignore the specific effect. So we need to allow for different intercept. Yeah. So for the second and the third estimator, we call random effect and the fit effect. Assume each unit have their own intercept, but they have the one slope only, share the same slope. The slopes still homogeneous. Homogeneous means the same slope, yeah, but they have their own intercept. Each unit they have their own intercept. To accommodate such heterogeneity, we decompose into two independent components. Yeah, I mean that our error term now consists of the lambda plus the mu. Yeah, so it's assumed that the mu is the ID and mean 0 and the variance equal to the sigma square. And then, okay, we have the specific effect, the lambda. Yeah, it's called the individual specific effect or unobserved heterogeneity. Is time invariant. Yeah, so I mean this value, let's say you want to assign a number or data for this heterogeneity is a fixed value. Yeah, it's time invariant. You can put 5, 5, 5, 5, 5 for the lambda throughout the year. Yeah, so hence it is not necessary to use the time, the t index in our equation. Yeah, so we can see now this is the equation, and then we can see the error term, the epsilon, now decomposed into the lambda I, no t, because it's the time invariant. The value is fixed over the time. Let's say you give the 10 or 5, 5, 5 for throughout the 10-year example, and then we have another error term. So this lambda is a constant across the individual. The value is constant, fixed value. And then the remainder error term, regular error term. And then we have the composite error term, total, composite error term represented by the epsilon term. So there are two options to estimate how to treat this lambda, the specific effect. Yeah, due to we have our data set, we have the specific effect. Mean we have the heterogeneity. So either you can use the random effect or fixed effect. Random effect assume the lambda are drawn independently from some probability distribution. And then a fixed effect, they assume the lambda are constant, mean the lambda is fixed. Okay, so I start with the random effect first. The lambda is assumed to be random variable with mean and 0. And the variance, and more important, is no correlation between the lambda and x. Yeah, because in this in the random effect model, no correlation between the lambda and the x. And the individual effect is characterized as a random. Yeah, so this is our equation. You can see that now we have the epsilon here. Epsilon consists of the lambda plus the mu. Yeah, this is the component. Then you can see that, yeah, you plug in the lambda I and the mu to substitute the epsilon. Yeah, this is our error term. So the error term consists of the lambda and the mu. So we can continue. So the lambda now is part of the error term. So this approach might be appropriate if observations are representative of a sample rather than the whole population. So there is a drawback here, yeah, because there's the lambda, yeah, because the lambda is part of the error term, they correlate with the error term, because when you that let's say t equal to 1 year 1, then you have the lambda. T equal to 2, you also have the lambda. T equal to 3, you also have the lambda. So each year, the lambda will be in the t. So therefore, they tend to correlate each other. So the random effect model, we should use the GLS, generalized least square. Because of this autocorrelation, ORS will be inefficient. So more seriously, ORS standard error will be biased, invalid. So what is required here is using the GLS. GLS can handle the serial correlation problem. Yeah, so the GLS estimator, also called the random effect estimator. So actually, the random effect is the GLS. We transform the data. So we transform the y and also the x by using the theta. So you need to get the theta. Yeah, theta mean right. So the theta can get from this formula, and then the yit minus the theta, then minus multiply the mean of the y. Then we have the also we need to transform the x variable as well, and then this is the theta. So you can see the theta. Yeah, we can simplify it. So we can cancel sigma square mean, sigma square mean. Then after that, you can see, yeah, no, yeah, this is the one. Yeah, theta, this is the formula how to get the theta. Then this is the beta random effect. So the random effect estimator use the weightage average within and between two-dimension variation in the data. So if all the individual have the same intercept, let's say the same intercept, they can share the same slope, mean that no heterogeneity or no specific effect, then they can move to the pool RS, they are the same, yeah. So they can share the same slope. So the sigma square lambda equal to 0. So you can see if theta equal to 0, the random effect estimator will become back to the pool OLS, yeah. So you just you can see cancel the sigma square mean, cancel the the sigma square mean. Then after that 1 minus 1, yeah, when the sigma square mean, no, sorry, sigma square lambda equal to 0, less equal to 0, we can see this one equal to 0. So t times 0 equal to 0. Then, of course, you can have the 1 here. The square root is 1. So square root of 1 equal to 1. So 1 minus 1 equal to 0. If I say the theta equal to 0, mean that no specific effect, no heterogeneity, our data set can be used the pool OLS to estimate. Yeah, so no need to differentiate whether we have the heterogeneity, yes or no. All right. I mean, if let's say the sigma square lambda equal to 0, then no heterogeneity or no specific effect, we can back to the normal pool OLS. So we can report the pool OLS result. You no need to report the random effect or the fit effect because our data set do not contain any specific effect.
Hello.
Okay, now
excuse me, Prof.
The third estimator strategy is called the fit effect. Yeah, so the individual specific effect assumed to be individual specific intercept, and then the more important, they have the correlation between the lambda and the x. I mean the specific effect, the lambda and the x, they tend to correlate. So this is called the fit effect model. So we treat the lambda as a constant for each individual. Mean that we move the error term, the lambda here, move to the constant beta 0 plus the lambda. So lambda now is part of the constant, but vary by individual. Yeah, let's say different
excuse me, Prof.
Different country.
Sorry for disturbing.
And we can see which firm or which country or which individual have the highest lambda. So example, this is the scatter plot for the, let's say the one that I showed you just now. So you can plot the pool or S. This is the pool or S. Yeah, you like to know heterogeneity. We can use the pool or S. But when you detect there is a heterogeneity or specific effect, we can't use the pool OLS anymore. We should use the fit effect. Right. So now you can see the fit effect. Effect model. The slope for KK is the same. No, for it's the same. No, for each individual only the intercept differ vary. Yeah. So you can see the intercept is here for the lowest group of the country or the group of the data, and then this one the highest one, they have the highest intercept. Yeah, followed by a second group, third group, and the last one. So the slope still the same. Let's say 0.5 the slope, but the intercept tend to be differ. This is called the fit effect. So we need to take into account of this bias slope when the fit effect are ignored. So this one is the pool OLS, and then the two line is the fit effect estimation line. You might wonder how come the random effect no diagram? Yeah, because the random effect is drawn from the different probability distribution. You draw this sample, maybe you get this result. You draw another sample, you might get a different result. Therefore, no one specific diagram to represent the random effect model. Okay, let's say, for example, we compare the four ASEAN countries, Singapore, Cambodia, Malaysia, Thailand. Okay, Singapore, okay, have the highest intercept, okay, because the high income country, let's say the X is the FDI example. So we have the 20, and then the 0.5, 0.5 is the slope. And then the Cambodia also share the same slope, 0.5, but the intercept is lowest one. So if let's say the X equal to 100, you plug in the X equal to 100 in your model, then you get the Y equal to 70 for Singapore. And the Cambodia, you only get the Y equal to 55. So this one is makes sense because, of course, different country, different unit, they have the different outcome because their intercept differ now, not the same. Yeah. If let's say you use the pool or S, both will get the same answer. 70, 70. Example, if let's say the intercept, the pool or S intercept is 20. Yeah. So of course they have this one due to the specific effect or heterogeneity. Mean they have different outcome when you compute the Y. Example. So this is the one. So you can see Singapore at the top here. Slope is 10. The slope the same, 0.5. Intercept is 20. Cambodia is the lowest one. The intercept example. So Y can be our income per capita. X can be the FDI example. But sometimes it's quite difficult to say the Singapore and the Cambodia, they receive the same amount of the foreign direct investment flow. But this is just an example. All right, so when the covariance between the individual specific effect in any regression is not zero, neither OS nor GRS provide consistent estimate. So there are two versions of the fit effect. One is within group fit effect, mean that we take the difference, we take the mean, and then the second is a least square dummy variable. We want to see the dummy, their intercept, yeah. So the within one, they find the mean for the Y, mean for the X, then they minus the variable, then they use the new variable, new series to estimate. So you can see Y minus the mean of the Y, the X also minus the mean of the X. And you can see the lambda minus the mean of the lambda, yeah. And the lambda I mentioned to you just now is a fixed value. Let's say the lambda is 555 throughout the 10 years. So the mean of the lambda also 5, because it's it's time invariant, yeah. It's the fixed value, So when you get the mean for the lambda, they also will be 5. So 5 minus 5, this component, the specific effect component, the lambda, that create the problem, will be eliminated, So no more lambda in our equation. Therefore, we can estimate the model. Then it's fair because all the individual, all the country, or all the firm, they do not have any specific effect or heterogeneity anymore. So now we can estimate the model and interpret the result, right? And then, so the above transformation is called the within or the time series transformation because the model use the within variation only. They find the mean of the variable, then each observation minus the mean, the y. So mean, let's say Malaysia will find the y mean, then each Malaysian data observation minus the Malaysian mean, y mean, the mean of the y. Then the Singapore, you find the Singapore mean, for the y, then you minus the mean, not mean that you find the overall mean, no. Each country, you need to get their own, and then after that, we have the, this is called the beta for the field effect. So I think within variation, the effect of the, the effect of the variable that do not change over time cannot be identified. Because when you use the field effect, let's say the variable is a fixed value, the field effect within group estimation will automatically drop the variable, that time invariant variable. And then the second field effect model is called the least square dummy variable. We can observe the effect, the lambda, meaning that we are not going to eliminate the lambda, but I want to see the value of the lambda. So let's say a set of the dummy variable di. Di is equal to 1 in the case of the observation relating to individual I and 0 otherwise. So I just demo direct. So for example, this we have 4 students. So this is the year, then there's the variable y and x1, x2. So D1 represent the student 1, dummy. D2 represent the student 2. D3 represent the student number 3. And the last one, dummy 4, represent the student 4 dummy. So there are large number of the individual, let's say I have 100. I need to have the 100 column, additional 100 column in my spreadsheet, the Excel. So using the least square dummy variable method directly is not so practical approach, given the need for a large number of the dummy variable. So when you include in the equation estimation, you need to have the n minus 1. Otherwise, we have the dummy trap. So let's say I 100 dummy, I need to include 99 only, n minus 1. Or else you put no constant, no constant, and can include all the dummy in your estimation. So these are the two major drawbacks. Mean that time invariant mean that the fixed value variable cannot include in their field effect. And then let's say too many unique or cross-sectional unique with too many dummy. And then maybe we include the, maybe we tend to lose degree of freedom. We need to move a little bit faster. So the question now is which one we need to choose, whether the random or the field effect. So there are two basic tests can help us. The first one is based on the Bush-Pagan test. This test to identify whether the data contain the heterogeneity or specific effect. So if let's say the data set contain this specific effect, we can forget the pool OLS. We focus on the random and the field effect estimator. Right? So I think that's one I think I can skip. So the hypothesis now, if let's say the sigma square lambda equal to 0, we support the pool OLS. If let's say the test reject the hypothesis now, then we conclude there is a heterogeneity or specific effect appear in our data set. So the LM test is easily to compute using this formula. So it's available in the Stata, or you also can compute using manually Excel as well. So then last time, this command is not available when I use the eView to conduct the workshop. Then I use manually like using the Excel to compute the LM test. So the distributed, it's a chi-square distribution, 1 degree of freedom. So okay, use the same formula, same model, the one used for the 10 Asian country data. So yeah, then I need to test whether is there any heterogeneity or specific effect appear in my data set. So this is the command in the data. So don't worry, I believe you have your own software or want to test, but the data is quite popular using in the US, UK, the university especially, they want to estimate the panel data. Yeah. So we can see this is the XTIG. IG is a regression, and then we include the XT. So the command start with XT is a panel data or the LD command. So you put the dependent and then the three independent, then the comma RE stand for the random effect. So this is the result. Yeah. Then after that, you immediately use the command. So the command for the Bush-Pagan LM test is a XT test 0. So you see the p-value, see the p-value. If the p-value less than the 0.05, yeah. So the p-value less than 0.05, this indicate that random effect model is more appropriate compared to the pool OLS because there is a country specific effect. Because this is a country level, I compute country specific effect. If let's say your sample is an individual or student, you can say individual specific effect or student specific effect, yeah, or heterogeneity. So the next question will be how to treat the country specific effect, the lambda, yeah. So yeah, there are two options here. Whether you want to use the random effect or the fixed effect estimator. Yeah, how to treat this specific effect? Yeah, we want to use the random and the fixed effect model because these two models can handle the heterogeneity. So we have another hypothesis. If let's say the covariance between the lambda and x is equal to 0, no correlation between the lambda and x, we support the random effect. And if let's say there is a correlation between the lambda and the x, the independent variable, so we will support the fixed effect model. So the next test, we need to use the Hausman test to test this hypothesis. Yeah. If we reject the hypothesis now, then we conclude the fixed effect is more appropriate, more preferable in this case. Okay, so this is the Hausman test. I don't think I need to go through the Hausman specification test to differentiate the random and the fixed effect. Yeah? It's based on the chi-square as well. Also look for the p-value less than 0.05. Yeah. Okay, so after when you run okay, now we run one fixed effect model. Okay, just now RE is a random effect, but now it's a fixed effect model. Okay, then after that you get the result. Next, immediately after that, yeah, this is the R square. Normally in the panel data, we are not going to interpret the R square so much because it consists of the time series as well as the cross-sectional data. Yeah. So the highest is when you convert to the 10 observation. Yeah, cross-sectional observation. You run in the 10 observation, they will give you the highest R square. So after you run this effect, immediately you need to estimate the store the fixed effect result. Then you run another random effect. And after that, you get the result. Then you need to use a Hausman fix. This is a Hausman test. So again, we look at the p-value. So if the p-value is less than 0.05, we reject the hypothesis now. Mean that we prefer the fixed effect because we reject the random effect. Yeah. So this indicates that the random effect model is not appropriate. And the fixed effect model is to be preferred, yeah, because they support the fixed effect model. Mean that, yeah, the fixed effect model is more appropriate, and we know that the fixed effect model, they have their own intercept. Okay, then I say that, okay, this is make sense, economic sense, because if we interpret in terms of the country specific, like the lambda can be the initial technology. Of course, different countries they have their own initial technology, like say the Japan, Singapore, South Korea, their initial technology is better than Malaysia, Philippines, Indonesia, right? and also in terms of the resource endowment, human capital, and so on that differ across the country. So it's argued that these are likely to be correlated, mean that all right, the lambda capture the specific effect, and we know that the specific effect can be the initial technology. So the initial technology is correlate with the GDP per capita, correlate with the FDI, either one, but we do not know. Yeah. So this is the correlation between the error term. So because the lambda is part of the error term, so it correlate the x variable. Okay. So they have the different intercept, and the F test reject the hypothesis now. Okay. Yeah. So okay, the F test also you can see common intercept and the different intercept. You can see the F test result. The the last row, the FP value also 0, equal to 0, mean they reject the common intercept, they conclude the different intercept. Yeah. So when different intercept, this is indicate that it's a fake effect model, not the random effect model. I think I'm going to finish at the top. Yeah. So this one is just a least square dummy variable. You can see their own each country intercept. I got 2 stand for Hong Kong. I got 3 stand for other country. And then I got number 8 is Singapore. And Singapore have the highest negative 2, because due to the 2007, 2009, the global financial crisis, I think that Singapore is most affected one. So the intercept assume that, okay, if other x variable equal to 0, what is the value of the y? Then the value of the y for Singapore is a negative 2.19. It's the highest one compared to other country. Yeah, so this is the intercept for each country. Right. So I think I need to move on. Then after that, okay, you need to do it manually. Then you can generate the country dummy, tabulate the code, generate the country dummy. Then you can include the country dummy in the model. Yeah. So I put the n dummy 2 until n dummy 9 or n dummy 10. Then after that, this is the result similar with the peak effect and the within peak effect, the coefficient for the 3 variable, with extra intercept for the country. Yeah. Or individual or the firm. If let's say your data is the individual data or the firm level data. So they are the same. You can see they have the F value the same, 35.4, and the P value also 0. Mean that it's a fit effect, support the fit effect, the least square dummy variable. The extra information we get the intercept for each country. Then we can see which country has the positive or negative intercept. Okay, after that, we need to perform the diagnostic check. Multi-collinearity, of course, no need, because you can try. Normally, no multi-collinearity issue. And then we need to check for the heteroscedasticity using the modified Wall test. And the serial correlation, we use the Woolrich 2002 serial correlation test. We can use the Watson, for the serial correlation, as well as we can use the outlier test to. Yeah, by the way, normally before we start to analyze, we need to check for the outlier, and then we can drop the outlier a few observation. Then the panel data become a Mellon panel. Yeah, become a Mellon panel data. The result tend to be better when you drop the outlier. So this is the multi-collinearity test. You request the dependent, independent. After that, you just put the VIF. Then they show you the VIF. So the VIF for the 3 variable, then the average is 5.67. So some textbook they say less than 10. Some textbook they say less than 5. So let's say less than 10, then there's no multi-collinearity, because this data set only have 170. Yeah, so it's not so large data set. You have more, I believe that the VIF value will become smaller, no multi-collinearity. And then for the heteroscedasticity test, you need to use the command is the TXT3. You can install the command. Yeah, the good news for the data, you can install any new command available online. You just install, connect to internet. Yeah, so you can see the p-value is 0, and again, yeah, so reject the homoscedasticity. We have the problem. of heteroscedasticity. And then in terms of the serial correlation, we use the Woolrich test for autocorrelation. You can install as well. Yeah. Then again, the p-value also show 0. Then we have the problem. As long as the p-value less than 0.05, we have the problem because we cannot, because we reject the null hypothesis. Yeah. No serial correlation. You can see here, hypothesis null. So make sure that your p-value for the diagnostic check is greater than 0.05. Yeah. Then this is the one that I get from the Daniel in the Stata journal. How to overcome the problem when you have the two heteroscedasticity and also the autocorrelation. Our example show two problem, hetero and the auto. So this is the command you can address to overcome the problem after you regress using the least square dummy variable, include the country specific effect, then cluster by the code. In the bracket is our code, yeah, or the ID. Or you can use XCIG, the fit effect, then cluster with the code. So I do the result. So this is the one. So I put all the variable, I put because it's a fit effect model, so we need to put the country dummy inside, then cluster the code. So this will be the new result for you to report. Later I will summarize in one table. And this one, you want to use the XCIG using the fit effect model, then just cluster the code. Then this is the result, same result. So finally, we can summarize in one table like this. So we start with the pool RS and compare the post-pagan M test. So reject. So we reject the pool RS, then we need to move on, whether use the random and the fit effect. And then the Houseman test, reject the random, support the fit. Then all the diagnostic check we need to perform for the fit effect model, right? So for the random effect is a GLS, and you no need to do the serial correlation. And
Excuse me,
all the tests,
Prof.
yeah,
Prof.
yes.
It's 11:53 now, and we have numbers of
I
questions.
finished.
Yeah.
I finished. Yeah. I think this is the actual. I think.
Yeah. Maybe if they want more explanations on the technicality, they can directly ask you, send you an email or something.
Yeah.
But thank you very much.
Final one. I just want to show you the
Sure.
software. They have see many estimators. See the longitudinal data or panel data. There's so many tests. Linear model, random coefficient of the GLS model, dynamic panel model, also the frontier model, the binary outcome, ordinal outcome, count outcome, sensor outcome. So these are the tests that estimator you can apply. Yeah. And so these are the references. So yeah, I have a book published by the UPM Press. Yeah, so in 2018, yeah. So you can obtain the book from the UPM Press on Shopee as well. So I think that's all I want to share. So I hope you can understand the detail about the LD analysis, compare this type of analysis with other quantitative analysis before applying it in your research area. I believe that each of you has your different area, different background, and the panel data analysis workshop also is available at the School of Business and Economics, University Puchong, Malaysia, through the EDL, Executive Development and the Industrial Linkages. From time to time, we have the panel data workshop. Yeah, so you are free, you can join. You want to learn something, you can join the workshop. So I think that's all.
Okay.
Yeah, thank you so much. So yeah. So if you have any question,
Okay, thank you very much. Yeah, we have a lot of number. We have numbers of questions. I'm gonna read the first two from Norlaila Mazura. The first question is, how LD analysis can be applied in qualitative research design? And in your opinion, LD analysis is it only applicable for quantitative research design?
Yeah, thank you for the question. It's a good question. So yeah, you mean that the qualitative one, let's say, you mean the survey type, the primary data, you can trace the individual, let's say maybe 1 year or let's say every month you give something to this maybe you give vitamin C and then you have the other control group they do not get the vitamin C example, then you observe this group and the other group control group so yeah, throughout the maybe 1 year or of course take a time when you want to do this longitudinal research. Yeah, you can record their health, the outcome. Yeah, so it can also apply to the qualitative research, but you need to collect the data not only one time, but maybe several times to observe the same individual. So you need to assign an ID so that you can know that this person, you can ask that person to fill out the information again. Then you can see any difference between throughout the year, let's say 1 year, 2 years, whether the outcome or the response has been different, especially what you want to see. Yeah. So it's also can be applied to the primary or qualitative research as well. But you need to collect the data same person over time. Mean that you need to distribute not only one time to fill out the data, the questionnaire, but maybe 4 times. Then you have the four observation, the T. Yeah. Then you can analyze the panel data. Okay, by the way, the minimum T is 3. Yeah, the time is 3. You cannot get 2 because 2 after you take the first difference to this year minus last year, then it will become 1 observation. When it become 1 observation, then we're back to the cross-sectional study, not the LD or panel data study. Yeah, I hope I answer your question. Yeah, is it the second question?
The second question is basically the same as the first question.
Yeah.
Because the conclusion is LD can be applied to both qualitative and quantitative research design. And
Yes.
the next question is, may I know in what circumstances do we need to exclude intercept during the analysis? Because as some studies I found, they didn't include intercepts in their model.
Oh, yeah. Some study it depend on the theory. Yeah, the theory because let's say the theory say that they start from the origin, the intercept. Did not go through the the intercept. Yeah, then no intercept. So this one is based on the theoretical explanation. Yeah, for example, in the area of finance, I think one model. Yeah, I think they start from start from 0. Mean they have no intercept. Mean their intercept is equal to 0. Yeah, then they have the straight line, the linear regression line, and then the intercept is equal to 0. Therefore, no intercept. This one we need to base on the theory. Yeah, you think that let's say other variable x, the independent variable equal to 0, then what is the value of the dependent variable, the y? Then you can have the intercept. Yeah, if let's say of course sometimes the intercept cannot be negative as well. Let's say the saving, let's say other independent variable equal to 0. Let's say your saving cannot be negative, and then the housing price also cannot be negative price, right? So this one depend on your study. Yeah. So you need to be careful whether you need to include the intercept, yes or no. The intercept is let's say we assume that other x variable equal to 0. What is the value of the y? Yeah. So the y whether is positive or the y equal to negative. So the prices, let's say negative prices, doesn't make sense. Yeah.
Okay. It's already 12:01. We pass our.
Take a longer time. I'm so sorry
Yeah.
because
But we have one more question, but I think to answer this question is going to take quite some time because it's quite technical. So I suggest Shah Kasim to directly ask this question to Prof. Lau. It's about generalized estimating equations versus generalized linear mixed model. It's still a debate until today. So maybe Shah Kasim can directly ask Prof. Lau through via email.
Yeah, yeah.
Thank you very much, Prof. Lau, for very insightful presentation. And we'd like to thank Kate again for inviting us. And thank you to all the guests, to all the viewers. If you join us after we have started, you can always rewatch this on CADE UPM YouTube channel. Okay, so I think that's it from us. Thank you very much, Prof. Lau. Thank you very much, Kate. Thank you very much, everyone. Have a nice day. Stay safe and good luck. Bye
Thank you,
bye.
everybody. Thank you for joining the webinar. Thank you so much, Kate. And also thank you, Afam, for moderating the session. Yeah, thank you so much.
Yeah, bye.
Thank you, Prof. Lau. Thank you, Dr. Afam.
Thank you, Dr. Dahlia. Thank you.
Thank you.
Sorry ambil masa lama sangat.
I think it's just on time, right?
Yeah.
Boleh lah, on time lah.
Chun on time.
Yeah. Dua
Afam is
jam.
good in monitoring.
Ya, betul. Dia bagi saya signal. Ya. So next time, kena bagi Afam jadi moderator lagi ya.
Hi.
So I think we are just waiting for everybody to leave. So if you want to leave, I think it's fine as well. So
Yeah. How many participant total Dr. Dahlia ada?
semua tadi about plus minus about 80.
80 lebih dekat Zoom, 30 lebih dekat YouTube.
YouTube. So about kalau dalam Zoom about 80 plus lah kan. So
Thank you.